This is Tim Hegarty with the Virtual Training Company C++ Fundamentals. We are now going to take a little deeper look at the fundamental of class member access, and this gives us the term encapsulation. Encapsulation allows us to have functions or methods, they're called in classes, and data members of the classes totally enclosed within the class unless we specify otherwise. Whenever we create a brand new class and don't say otherwise, the members, methods, data, everything that's in there is private. That's by default. The class members can then only be used by the class member functions. The methods that are built into the class can only get to that data that's part of inside the class, or classes specified as friends, and we'll take a look at that in a little while in a different video. We can specify public access. Public access means that any other function can get to or call those class members and methods. It's totally open. Protected is kind of a combination. Protected access says that the class members can be used by the member functions of the same class and by any derived class member functions. So if we have a higher level class of car, let's say just a car, and then we derive a class below that of Ford, then the derived class could make use of things that are in the car class that are above it, that it has been derived from, but nobody else could get to it. So you kind of have a family tree going on here of classes when you have derived classes like that. Here, for example, is a simple my class being created. All of these members, X, Y, and Z, are private because we have not said otherwise. So only, and we don't have any here, we haven't defined any methods, but only methods of my class would be able to work with X, Y, and Z and store things in them. Gives a very tight black box, or encapsulates the data within the class. Now here we have used the public keyword in this class, and X is still private because it comes before the public access specifier. Y and Z, however, are now public, so any other function, anything else that wanted to get to myClass.y could get there and work with it. And then finally, here's the protected. We have int X is still private, int Y is now public, and we have the protected is Z. We can work with functions within my class, methods within my class can work with Z, and anything that is derived from my class can work with Z, but nothing else can get to it. So it's encapsulated along the lines of the family tree. And this is class member access, which implements the fundamental of data encapsulation within object-oriented programming. This is Tim Hegarty with the VTC C++ Fundamentals. Let's talk about some friends. Friends are other functions that are allowed to operate on our class that we're defining, on our class's private and protected members. Because remember, we have public, private, and protected. And private and protected are not visible to the rest of the world in general, but public are. Now, we can, though, in a class say that this is a friend. So let them do what they need to do with private and protected members. A friend may be a method in another class, or it can just be a simple function out at global scope. Either way is fine. The friendship is declared in the class that's giving the friendship away, that is defining the friend, because that way it maintains control over who is a friend and who isn't. Let's take a look at a piece of code here. And here we have a class called point, and within this class there's a public area. We're going to skip over the friend here for a second. There's a public point which has a value, and then there's a method here that's a print private, and it's going to print out the value of this m sub I, or m underscore I, which is a little integer down here that's private. So nobody can get to that because it is private until we make a friend function up here. So here's a friend declaration. No return. This function called change private, it'll be given a point reference. This change private is allowed to do whatever it wants with the private members down here. Now here's the actual definition of change private. And when we're defining it in here, definition and declaration, it's an inline. And all we're going to do is increment the value. We'll just bump it up by 1, and that's that. So we come straight to the location, add 1 to it. Down here in main, here we make a new point. This is an S point. We say that sPoint.printPrivate. So we're going to find out what's in there. We're going to call change private, which we really should not be able to do. Only this friend declaration up here allows us to change that. And then we'll print private again. All right, pretty straightforward. Do a quick Control F5, and there's 0 and then 1. Not very impressive, but it does illustrate our point here that this, so to speak, this class point has allowed or created a friend which is able to get to this private member and do something with it. Now that breaks down some of our encapsulation concept, so you have to be careful who you define a friend and just what that friend is allowed to do. So that is the concept of defining a friend method in our encapsulation topics here. This is Tim Hegarty with VTC C++ Fundamentals. Let's take a few minutes to talk about base classes. A base class is a class that other classes are derived from. So let's say that we have a base class of a printed document. A book is a printed document, so it is derived from printed document. Okay, so printed document is the base class. Book is the derived class. A paperback is a book, and it is a printed document. So a paperback is a derived class, and it is derived from what is now a base class to it called book. So book is both a derived class because it's derived from printed document, and it's a base class because paperback is derived from it. As you can see, there are bound to be properties of a printed document that will apply to a book, and then there's information about a book, like maybe an ISBN number or something like that, which would not necessarily exist in a printed document, but those members of book would apply to a paperback as we go down the list. And a paperback will have some members that it gets from printed document, like maybe pages or covers, front and back covers, that books would also have. So this is how we work inheritance. Inheritance is the key word right here, and we have book inheriting things from printed document, and we have paperback inheriting members and methods from both book and printed document up the tree. So that's base classes. Now, what we want to also get in on here is public, protected, and private base classes. When we define a derivation, when we declare the new class derived from a base class, we say what access level that we want to make the base class's members in this new derived class. If we say public, the base class's members will maintain their original level that they had, whether they were public, private, protected, as they come through into the new derived class. If we say protected when we create the derived class, then the base's class members will also be protected, whether they were public or not. In their base class, they will now be protected in the derived class. When we say private, then all of the base class members will be private in the derived class. So they're all private as it comes down through. Now we're going to take a look at some code here, and there's a lot of other things going on in it. And when we get to our next chapter and we talk about derivation syntax, how all of this works, we'll get into this in more detail. But right now, I just want you to take a look at a little bit of public and derived, or derived classes, base and derived classes. So here we have a class called mother, and it has a public section, and that's the constructor. And this is a constructor with a slightly different interface, a constructor with a parameter coming in. And now here we have a new derived class. As you can see, this is a class called daughter, and it is derived from, that colon is what makes the derivation. It's derived from mother with the public class. So these things that are public will be available to daughter as well, these constructors. And when daughter is constructed, when you create a new daughter, not only will the daughter constructor be called, but the base class constructor will also be called on up the tree here. Now here we have a class called son that is also derived from mother, and here you can see that we have a son constructor with no parameters, and here we have a slightly different son constructor with a parameter. And what it is saying is that when the son constructor is performed, a specific base constructor should be performed. If you don't specify, like here in this daughter int a, the daughter constructor with an integer or with a parameter will be performed, but the mother constructor up here will be performed without parameters. The default will be performed. You have to override that down here. This is what we're doing. We're saying that when son is called and it receives a parameter, we want to make sure that that parameter gets passed on up. Again, we'll look at this in more detail when we look at derivation syntax, but that's what's going on here. And then we create new objects of type daughter and type son and return 0 here. We won't even bother to run this right now, but I just want you to see this is where the public, private, and protected base class and derived class keyword goes. So that's base classes and their access, public, protected, and private. This is Tim Hegarty with the virtual training company C++ Fundamentals. We now want to take a look at constant expressions. Now you already know about constants and how to create constants so that you don't have magic numbers all over your code. That's a pretty basic fundamental from C programming itself. What we want to take a look at are the constant expressions in C++ and how they work. We've got a little function here, and what we're going to set up here is first of all a little character array that will stick the name norm in, and then we're going to create a pointer to a constant. So we have constant char star PC, and then we'll set it equal to some address to S, or the location of S. Now here we cannot then say that PC sub 3 is equal to G. We can't change the value that is within S because PC is a pointer to a constant. So that tells us that we are not allowed to do that. Now S itself may not have been defined as a constant. It may have been defined just normally as some array of memory out there and declared and defined. But PC is a pointer to a constant, so it cannot make that change to S. So that's when it's useful to have pointers to constants so that you don't accidentally change something. Now here we can change the value of PC because it is not a constant pointer. It is a pointer to a constant. Okay, so does that make sense? Here we have a constant pointer. So now notice a little bit of a difference here. We have character pointer constant CP equal to S. And of course, since it is a constant pointer, it has to be initialized as it's defined so that we get the initialization over with at the front. We can say that what CP points to, the third byte of it, is equal to A. That's okay because S is not the constant anymore. The pointer is the constant, so that we cannot move the pointer and move it up and down an array of arrays or anything like that. CP equals P, we cannot change that, so that's an error. Can't change the constant pointer. Now here we have a constant pointer to a constant, so that we can use the information, read it, but not accidentally change the pointer and not accidentally change the value that we're pointing to. So it's a constant character pointer to a constant CP, and character pointer C equals S. Okay, so that's a constant pointer to a constant. And I see a little typo there. Take that space out. Star constant CPC equals S. There should not be two values right there. And there we say CPC sub 3 is equal to A. That's an error because we know that both of these are constants, that CPC is a constant pointer to a constant. So can't do that. And that will be an error, and we can't change the value of CPC either Can't change what it points to. We can't change it because it is a constant pointer to a constant. So that's what C++ gives you over and above the typical constants that we're aware of in the C language. Hi, this is Tim Hegarty with the virtual training company C++ Fundamentals. We are looking at now static cast operators. A static cast operator is used to force a cast, and you as a programmer have to make sure you know what you're doing with this. And since this is just a fundamentals area, we're just going to look at this for a minute because you're stepping over or your bounds and could literally overstep your bounds by using a static cast to force various kinds of pointer conversions, which we'll see in the next slide here. But first of all, let's just say that we have a little bit of a program here that is going to allow us to show static cast operators. So here we have a character ch, an integer I, a float f, and a double. So we can do a static cast, and you can see we're going to cast a char, and that's of I. So we're going to take this integer I and we're going to force it to a character and put it into ch. And a static cast does not do any kind of runtime checking or anything else to make sure that this is sensible or legal or even possible. So you're on your own when you use these. And here's another one. We're going to static cast to a double from a float. So we have double inside the less than greater thans, and we're going to take our float, cast it to a double, and here we're going to do a static cast of a byte, and you can see we have a new type there, which we did in a type def, so that's just an unsigned character. So we're going to take ch, which is our normal character, and force it with a static cast into I, and that will be an implicit cast there, which we've seen in other parts of our tutorial, but rather than the forced static cast. Now here's where we use a static cast to cast pointers up and down a class hierarchy. We've created a class called B, and then we've created another class called D, which is derived from B. So D is a superset of B. It is larger and could have, most likely does have, more methods and members in it than B had. So we have to be careful in banding about pointers between these two. So now we have a function called f, and it will take in a B pointer called PB, pointer to B, and it will take in a D pointer, pointer to D, PD. Well here, this is an unsafe static cast, but you can do it. No runtime check is performed. What they're going to do here is they're trying to cast PB, which is a pointer to B, as if it were a pointer to D. And remember, D is larger. It takes up different memory. It has a different layout and could have different access specifiers to its methods and members. So by doing this, the compiler will do it and put this in PD2, but if you use PD2 and this did not point to the exact structure, the class, which we know are just superstructures from C, if you don't point to exactly the right kind of structure, you could blow the world away. Now down here, this is okay. This is a safe conversion because we are taking the D pointer, which is larger, and casting it down to a B pointer because the B pointer is within and wholly contained by the D pointer, or by the D class. The B class is wholly within a box within a box. It is within the D class. So it's okay to cast a D pointer to the bigger box as if it pointed to the smaller box because we know that that will fit, and we can put that into PB2. Okay, so just be careful with a static cast, and again in the fundamentals I hesitate to even bring it up, but it's something you're going to see in code and you want to see what it's doing. It is forcing a cast of an expression to this type and then returning the result of that type. This is Tim Hegarty with the Virtual Training Company. We're doing C++ fundamentals videos here, and we are now taking a look at dynamic cast operators. And in this case, we're looking at something called an upcast. Now, we already took a look at static cast operators, which we understand now are type conversions, casting, that are explicit. They're provided by the programmer, and there's no type checking going on. I'm sorry, there's no runtime checking going on to make sure that it's a valid, sensible thing to do. This dynamic cast operator requires runtime checking to be enabled when you're compiling, and it will perform the runtime check to make sure we don't do something silly. So here we have a class B, and we have a new class C, which is derived from class B. So that's a box inside a box. Class B is a smaller box, and then class C is a larger containing box, and then class D is yet another larger item, which has starts out looking like a public C, the class C, and then has its own methods and functions and such members added into it. So we're building a hierarchy here of B to C to D. Now in our function here, our void F, it is going to receive in a D pointer called PD, pointer to D. If we want to make a new C pointer, so that's the smaller class, fits inside a D, PC equals a dynamic cast to C pointer of a PD. That's okay because we're doing an upcast. We're moving from the larger box to a smaller box, and that is sensible. Something that already points to the large item can easily point to something that is within the box. All right, so that's good. Now here we're doing a B star, and that's a pointer to B. We want to make a new pointer to B, and we're going to cast a B from a PD, from a pointer to D. So we're making yet a smaller box. We're using a pointer to the larger outer class D, the derived class, which was derived from C, which was derived from B, which is the base class back here. And this is also okay, because B is an indirect base class, because we worked our way back up the chain to get to the uppermost base class. So that works as well, and the compiler has protected us. Now here's using a void pointer. Here we have a class A and B, whatever they happen to be. Here's our new function, and here we have A star PA, that's a pointer to A, and it will be initialized with a new A. So we go out and create some memory and make this thing. Here's a B star. We're defining a pointer to B, and that's a new B. Go to memory again, create the thing, construct it, and so on. Now, here is a void pointer, PV. And PV is going to be equal to the dynamic cast void pointer of PA. That's just fine. Using void pointers is perfectly legal for all this. Now, there will be some runtime checking to make sure that this pointer can accept the conversion of this PA, and we know that it can because it's a void pointer, so that's fine. And here we say that PV is a dynamic cast of void pointer of a PB, also just fine. Using the void pointer is perfectly acceptable because we don't have the issues of assigning a pointer to the larger derived class into a pointer of something smaller, which it can't handle that. Now here's a downcast. This is going the other way, down the hierarchy. Here we have B, and then we have class D, which is derived from B. So D is the larger one, the containing class, and the derived, and B is the smaller. So here we make a new pointer to B, is a new D. Now that's not very clear, but it's all right. So we make this new D class and put it into PB, or the address of it into PB. And here PB2 is we make a new B class, a new base class, and assign its address into PB2. Now we're going to do our dynamic cast. So now we have a D star, which is a pointer to D, and we're going to cast a D star. We're going to take the pointer to B. Now it actually points to a D already, so that's okay. And we're going to cast that to a D pointer and put it into PD. Acceptable. But now we're going to get into trouble over here. The dynamic cast is going to try to take PB2, which we know from up here points to a B, a smaller item, and we're going to try to cast it to something pointing to the bigger box. That's not going to work because we can't take the internal base class pointer and try to cast it to point to something bigger than itself. The small box will not fit outside the large box. Okay, so we get to PB points to a B, not a D. That's an error. So dynamic cast will return a null, and the operation will not complete. That's why dynamic cast is going to prevent us from doing something illegal. So that's dynamic cast operators: upcast, void pointers, and downcast. This is Tim Hegarty with the VTC C++ Fundamentals. I want to wrap up our conversation on operators here by looking at the C-style cast operators and confirming that they are still there in C++. We have two kinds of basic conversion. We have an implied or implicit conversion, and there you see we have a character A equals 100 and B is an integer, is equal to 0, and B equals A. A will be promoted, a number of bytes will be bit extended to the left to get character A to fill out the multiple bytes of an integer B. So that's an implied conversion that the compiler and the language will take care of for us. An explicit conversion is one that we want to be sure that we have control over. We know exactly what's going on. And there are two types of those. There's a C type and there's a new C++ functional conversion. Again, we have our character A equal to 100 and we have our integer B equal to 0. Here B equals int inside parens of A. So that is producing the explicit typecasting of A from a character to an integer. So the A will be changed to an integer value, again bit extended to the left and so on, before it's provided for B to be assigned into B. The second type is the new functional conversion we call an integer function against A, and that will result in the integer value of A, and A was 100, so that'll produce 100, which will be put into B. So our C-style cast operators are still there with one slight change for the functional conversion type of both implicit and explicit conversions.